Hello everyone. We know that when a magnetic dipole is placed in a uniform magnetic field, according to its orientation, it will experience a torque. And depending on the orientation, since it experiences a torque, some work is done on the magnetic dipole by the magnetic field, and because of which it gains a potential energy. So, when a magnetic dipole is placed in a uniform magnetic field, it has a certain value of potential energy, and we are going to calculate the value of potential energy in this video. Okay, so let us see how it is done. Potential energy of a magnetic dipole when the magnetic dipole is placed in a uniform magnetic field. So let us first consider the diagram here. You can see two poles are there. One is the north pole and another is the south pole. We can consider it to be the poles of a horseshoe magnet, and in between we have magnetic lines which are given by the long horizontal lines which are parallel to each other, showing that the magnetic field is uniform in this region. So here we have placed a bar magnet, or we can say a magnetic dipole, which has a south pole and a north pole, and the dipole moment is acting in the direction from the south to the north of the pole. And you can see that the angle made by the dipole with the magnetic field is theta. So theta is the angle which the dipole makes with the magnetic field. And since this dipole is kept in the magnetic field, if you remember when we considered electric dipole placed in a uniform electric field, in that case, if you can remember, on the charges which are placed at the two ends of the dipole, minus q and plus q, they experienced a force QE. Now here in the magnetic field B, the magnetic poles will experience a force MB, where M is the pole strength, it is given by small m, and B is the magnetic field. So the situation is quite analogous when we consider the case of electric field. In the electric field, the value of force is given by QE. In the magnetic field, the value of the force acting on the poles are given by MB. M is the pole strength, B is the magnetic field. And you can see in the north pole and in the south pole, the directions are opposite, because this north pole will attract the north pole of the south pole of the bar magnet by a force MB, and this north pole of the bar magnet is being attracted by the south pole of the magnet here, strong magnet, by a force MB. So both the forces MB and MB, they are acting in the opposite directions, but their line of action are different. Okay, so you need to understand this, that what exactly the line of action means here. See, when we are considering it, the line of action, you can see that there is a particular distance or perpendicular distance between the line of action. MB and MB, they have a distance of NA, perpendicular distance between the two forces. So the value of torque will be given by, let me explain this in a bit different way. Suppose this line which I am drawing here, this represents the perpendicular distance between the two forces, which is given by NA. So the value of torque, we know the formula for torque. The torque is given by either force into the perpendicular distance between them. Now the either force is MB and the perpendicular distance NA, which will be given by 2L sine theta. So MB into 2A sine theta. So that gives the value of torque, which is capital M B sine theta, where capital M is small m into twice L, that is pole strength into the length of the dipole. So the value of torque is given by mb sine theta, and this is responsible for rotating the dipole. Now, when the dipole rotates, as given in the diagram, it rotates in the clockwise direction, and it will try to align itself in the direction of magnetic field. Okay. So, in vector notation, you can see here m is along the axis here. This is a direction in which mx, I am showing it by red ink here, you can see. This is a direction of magnetic dipole moment, and the direction of magnetic field is here, which makes an angle of theta. So if the angle is theta, so mb sine theta in vector notation can be written as m cross b. So in vector notation, the value of torque will be m cross b. Tau is equal to m cross b. So I hope the value of torque is clear. Now on the basis of torque, we are going to actually calculate the value of work done. So to understand the concept of work done, we always do a similar method by first finding the small work done to rotate the dipole by a small angle d theta. So we are going to find the small work done. So the value of small work done, since in the rotational motion it is force into displacement is in linear motion. So in rotational motion it is torque into angular displacement, tau into d theta, where d theta is the small angle by which the dipole is being rotated. So we can write here the value of torque we will put here, that is mb sine theta d theta, where sine theta is the angle which the dipole makes with the magnetic field. Now you can see here the total work done. We have calculated the value of the small work done. Now the value of the total work done will be given by the integration of the small work done. So since you can see the integration in which the variable is theta, so theta 1 is the lower limit, that is the minimum value of theta, and theta 2 is the final value of theta. So theta 1 is the initial value, so we call it lower limit of theta. So we can see that when the dipole is rotated from an angle theta 1 to the final position where the orientation is theta 2, so the total work done will be integration from theta 1 to theta 2 mb sine theta. So integration of sine theta, mb will anyway come out, so integration of sine theta is minus cos theta, and we have taken the limits here. So minus sign comes out, it is minus mb cos theta 2 minus cos theta 1. I hope this is very clear to you, and this is the value of work done which we are getting, where theta 2 is the final orientation, theta 1 is the initial orientation. Now see, therefore here we are getting the value of work done, total work done, which actually represents the potential energy, and the formula comes out to be minus mb cos theta 2, theta 2 is the final orientation, minus cos theta 1. Now here we will consider one thing, that the initial orientation is such that the angle is 90 degrees, so that it experiences a maximum torque. So when the angle is 90 degree, which experiences a maximum torque, so the value here cos theta 1 we will put as 90 degree, so cos theta 2 will be represented at theta only. So the equation now becomes minus mb cos theta 2 is replaced by cos theta, and cos theta 1 is cos 90, which is 0. So we have minus mb cos theta. So this is the value of potential energy that we are obtaining, which is the total amount of work done to rotate a body from its rotate a magnetic dipole from its initial orientation of a 90 degree to a final orientation of theta. So the total or the net potential energy gained by the dipole will be minus mb cos theta, and this can be represented in vector notation, which can be written as u is equal to minus m dot b, because we know that dot product of two vectors m and b is given by mb cos theta, so it will be minus mb cos theta, right? Now see, we will consider some conditions here, and those conditions will be, first condition is when the value of the final orientation is 90 degree. So theta is 90 degrees, so the energy which the dipole is having will be minus mb cos 90, and cos 90 is 0. So when the dipole is perpendicular to the magnetic field, its potential energy is 0. That is, it doesn't have any potential energy. Now, to calculate the potential energy of a dipole at any position making an angle theta, with its initial position given by 90 degree orientation, then u will be minus mb cos theta 2 minus cos theta 1. Theta 1 if we consider as 90 degrees, so we have the final relation minus mb cos theta, which we have already discussed. Now another condition we will consider, let us consider that the value of theta is now 0 degree. Now you need to understand it very clearly. If the value of theta is 0 degree, it means that the direction in which the magnetic field is acting, this is the direction in which suppose the magnetic field is acting, and we are having a dipole which is in the direction of magnetic field. Its dipole moment is in the direction of magnetic field. This is south and this one is north. So dipole moment is also in the same direction. If m and b are in the same direction, so the angle between them is 0 degree. If it is 0, cos 0 is 1. So we have minus mb, which is the minimum value of the potential energy. And in this condition, when the potential energy is minimum, the dipole is considered to be in its stable equilibrium position where the potential energy is minimum. If you want to rotate the dipole in any possible direction, suppose you rotated it in this direction and you leave it, it will again come back to its stable equilibrium position. Okay, so I hope this is very clear to you. Now, the last option that we are considering here now is when the angle is 180 degree. The angle 180 degree means it is the situation when we have the dipole in a direction which is given by, let me show it here by drawing it. Now here is the north pole and this is the south pole. So the dipole moment is now in the direction opposite to that of the applied magnetic field. So the angle between them is 180 degree and cos 180 degree is minus 1. So the value of the potential energy is maximum. So maximum potential energy means it is in unstable equilibrium since it has a maximum potential energy. And if we displace it, if we displace its orientation, like if we change its orientation, it will never go back to its original position where it is in the unstable equilibrium, but it will come to the stable equilibrium position only. So you can see that in stable equilibrium, it is set stable equilibrium because it has a minimum potential energy, and if we displace the orientation, then it will regain its stable equilibrium position. It will come back to its stable equilibrium position. But whereas in case of the orientation, if it is 180 degree, then it is the unstable equilibrium where the value of potential energy is maximum, and if you disturb that position, then it will not come back to the unstable equilibrium, but it will in fact go back to the stable equilibrium position. So I hope this is very clear to you. So let us quickly see one of the numerical here. Suppose the current flowing in a plane circular coil of radius 1 centimeter having 100 turns is given. The coil is placed in a uniform magnetic field is also given. You have to find the in stable equilibrium and in unstable equilibrium, you have to find the potential energy. Okay, so this can be done in a very simple way. The value of magnetic dipole moment you have to calculate, which is NIA, INA and N, all the values are given. And after that, what you will do is, for stable equilibrium, the minimum value is minus mb cos theta. Theta is 0 degree that you need to calculate, and then you have to calculate for uh,